Okay, so I know that these videos are coming kind of slow. I've had all kinds of problems, um, but it looks like they're going up on YouTube now because that may solve my problems. Anyway, here comes another video, and this is something that maybe I should have done this a little while ago, but it's still a good time for it. Um, there are infinitely many prime numbers. Oh, a little out of focus. There we go. There are infinitely many prime numbers. And that's not an obvious fact. That requires a proof. And this is probably one of the really old, one of the oldest probably proofs in math. It's a really classical proof. It's due to Euclid. Um, well, okay. I'm probably wrong when I say oldest. Math is a lot older than Euclid. Anyway, I'm not a math historian, but this is old. Um, so let's prove that there are infinitely many primes. So this is going to be a proof by contradiction. So suppose for contradiction that there are finitely many primes. And let's say, if we're going to assume it's finite, why don't we really put a number on it and say there's a total of n primes? And let me emphasize only, meaning these are all the primes. Say P1, P2, up to Pn. Now, consider, oops, that's not how you spell consider. Consider the number, oh, I don't know, say k. That's just going to be, I'm just going to multiply all of these primes together. P1 times P2 times P3, dot, 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 all the way up to P sub n. And then I'm going to add 1. So that's k. So what am I going to say about k? Well, we know, due to the fundamental theorem of arithmetic, k has some prime factorization. And since these are the only primes there are, like, in the world, the prime factorization of k can only involve these primes. So if we were to write the prime factorization, which I could say that I'm going to write it down, but there's no point in writing down supposedly what it is. Its prime factorization would consist of prime numbers, and these are all the prime numbers, so it must have some of these in it. In other words, k must be divisible by some one of these, say p sub I is one from 1 to n because there's only n of them. But this is now a contradiction because we'll see that k can't be divisible by any of them. P1, P2, Pn plus 1. So if this is divisible by p sub I, then it should be congruent to 0 modulo p sub I. That's what it means to be divisible by p sub I. It's congruent to 0 mod p sub I. But if I do this mod p sub I, look, this is a multiple of p sub I. So actually this number is congruent to 1. this part is 0, and then this 1 makes it 1. Right, and this is just, so let me say this another way, just in case people didn't get it. This is congruent to 1 mod p sub I because, look, I can check it. What does it mean? For this to be congruent to this modulo this means if I subtract them, and if I subtract them, whoops, sorry, I didn't mean to write that. If I subtract them, the 1's just cancel, and all that's supposed to be is if I subtract them, it's a multiple of that. And it is, because this number is P1 through Pn, so Pi is in there somewhere. This is a multiple of P sub I. So we have a contradiction, because this is not, it was supposed to be congruent to 0 mod P sub I, but it was actually congruent to 1, which is not the same. So that's it. We got our contradiction. So there can't be finitely many primes. There must be infinitely many.